Grade for this isn't actually in Blackboard.
Yep, I just wrote it because you were turning in late. I have a note of it.
Oh, okay.
Yep. Okay. Okay, some reminders. There's no lab this week. Homework number 4 is posted on Blackboard. It is due next Wednesday, so not this coming Wednesday, but a week from then. And your first test will be a week from this coming Friday, so almost 2 weeks from today. We will review, next week from it. Also, there's no class this Wednesday or Friday because I will be at a conference. And no office hours this Wednesday. We'll have office hours today. If you have questions, and I'll have office hours next week for help with your homework. Yes. Yes. We should cover the rest of that today. If we don't get to the very end parts of that, then I won't question you over the very end parts of that on that test. But there is a problem doing that on your homework that relates to that. I probably will not post an actual practice test, but I may post some extra problems to do, just not fully in that format. I haven't decided yet. One of the two. I'll either give you extra problems or. Yes. So we will review in class at least next Wednesday, maybe part of next Monday too. Okay. Let's move on. Some days it wants to scroll, and some days it doesn't. There we go. Okay, we're going to be using our Routh Hurwitz criterion today to design controllers for a system. So we've been talking a lot about how we can analyze controllers, analyze whether a whole system is stable, that kind of thing from it, analyze whether it's second order, first order, third order, fourth order, their damping ratios, their natural frequencies. Talked about a lot of things we can talk about of our systems, but we're now going to move a little bit more into the design of our systems. So we're going to learn how to use Routh Hurwitz criterion to design a proportional controller to make our system stable, and a proportional integral controller to make our system stable. We'll be talking more about these, what are called P and PI controllers. We'll also get into a PID controller, which is a proportional integral derivative controller, which sounds like they kind of cancel each other out, but not really in the way you think. Later on in this semester, but right now we're just going to learn how to use Routh Hurwitz stability if we put these things in to ensure our systems will maintain stability. With that, we'll also talk about at the verge of stability, where we get marginally stable systems, what our oscillation frequency is for a system, and our characteristic equation that is helping tell us this characteristics for stability from it. So, designing a system for stability control. If I start with this block diagram, which if the K wasn't here, you kind of ignore this block K and you just had this block, then we've done something like that before of using Routh Hurwitz criteria for evaluating based on this transfer function what its stability is. What was the first thing we did, or we had to do, if we had a transfer function in a closed loop feedback system like this, before we could put it into Routh-Hurwitz criteria to evaluate it? What do we have to do with it? Could I put in just this denominator like this into my Routh-Hurwitz array? No, why not? Because there's a negative feedback loop, and that negative feedback loop changes what the equivalent equation will be if I were to get this down to just a single block of a transfer function that goes out without a feedback loop, right? That transfer function changes based on that feedback loop from it. So I have to calculate what this new transfer function is. So I'm going to do the same thing here, still just negative feedback loop. The only extra thing I've added into here is some block that my system goes through that has a factor k. So we're going to call this k a proportional controller. It's basically something that could make a gain. We talked about gains in op amps and sensing and measurement. It's just something you multiply your input by to get your output. This acts like a gain controller here, or a proportional controller. So when I have that, I need to come up with what's my equivalent transfer function, and then what's the characteristic equation from that transfer function. So remember, our general equation for converting a feedback loop into an open loop system here is that I take my forward gain over 1 minus my loop gain, and that gets me my equivalent transfer function. Right? So my forward gain here would be what? How would I calculate my forward gain for this system? Forward gain is what I take from my input, and if I just went in a straight path to my output, what do I go through? K times that fraction. And if k is just a constant, then there's no reason to be scared of k. I just get to treat it like a constant variable and multiply everything by k from it. So my forward gain here is just going to be 2k over this whole thing, s to the third, plus 4s squared, plus 5s, plus 2. Now I have to do over 1 minus my loop gain, but my loop gain has that negative sign, right? Because it's a negative feedback loop. So it really becomes 1 plus our loop gains, like we have. What's my loop gain? What gain do I have going all the way through here and all the way back? I've already taken care of the negative sign by making this plus instead of the negative here. But it's the same thing, right? I'm just multiplying by the same thing. So I have 1 plus 2k over s cubed plus 4s squared plus 5s plus 2. That looks like a really messy fraction. What do I do to make it prettier? Multiply by something on top and bottom. And what am I going to multiply by? Multiply by this whole denominator here. So s cubed plus 4s squared plus 5s plus 2. Don't scroll. And s cubed plus 4s squared plus 5s plus 2. Okay, so what does that get me? On top, I now just have 2k. These cancel out. And on bottom, I get 1 times this whole thing. So I'm going to write that whole polynomial again, s cubed plus 4s squared plus 5s plus 2. That's really just taking 1 times it. And then when it gets multiplied by this term, the denominators cancel out, and I get plus what? Plus 2k. Okay. Or again, my little trick, if you don't like going through that each time, if there's nothing in your feedback path, then all it really does is it takes your numerator, stays the same, multiplying on top from what you had of just this transfer function. So in this case, I just got 2 times k. And then my denominator will be this term plus my numerator. So it was the same denominator, I just added my numerator with it. That's what happened with that one. Okay, so what's my characteristic equation here? It is just this whole denominator term. S cubed plus 4s squared plus 5s plus 2 plus 2k, where 2 plus 2k is my whole constant term, or things that are multiplied by s to the 0, right? There are no s's with that. This equation, again, is different than this equation. it changes where those poles are, and therefore it changes my whole thing in Routh-Hurwitz. So I had to go through this process first before I can get to this is my characteristic equation. Okay, let's put this equation in a Routh array. So my Routh array is going to have third order, so s to the third, s squared, s to the 1, and s to the 0. And what numbers am I going to put in? For s to the third, I have what coefficient? 1. For s to the second, I have what? 4. For s to the first, I have, for s to the 0, I have what? 2 plus 2k. That's where that just comes in to be a little bit. Again, don't be scared of the k, it would just be a constant. Later on, we can plug in for whatever the heck that constant is. Right now, I don't know what it is, so I have to leave it as a variable from it. Okay? How do I calculate my next row, my s to the first row? Do what? I'm doing my negative determinant, so positive determinant will go this way, negative starts this way and first. So 5 times 4 gets me what? 20. And then minus, going this way, minus, I'm going to write it, I'm going to spread my minus sign out just so I don't forget because I'm really bad otherwise at doing that. Minus 2 minus 2k over what? Over 4. What about my next term on that row? 0, because I would have this times, there's nothing over here, they're implied zeros. Okay, what would my s to the 0th term look like? I would have this number times this number, which may seem scary right now, right? But minus 4 times 0, that's nothing, so that's okay, over this whole number. So if I had this times this over this, what does that get me? 2 plus 2k. So it's nice when they simplify a little bit. Again, k was just some constant. I want to solve or design this system that has some proportional controller in my closed loop negative feedback system that can multiply by some value k and still keep my system stable, or perhaps make it stable if it wasn't before from it. So what should k have to be? What are the limits on k? And first of all, I'm going to take 20 minus 2 and really just say that's 18 minus 2k if you're okay with doing that. And we know that to be stable, our terms in the first row, the first column have to be greater than 0, right? So 1's greater than 0, 4's greater than 0, but I need this term to be greater than 0. When will this term be greater than 0? So an 18 minus 2k over 4 has got to be greater than 0. So you multiply by 4, that doesn't do anything. 18 minus 2k has got to be greater than 0. So negative 2k's got to be greater than what? Negative 18. And then k has to be what? Less than 9. Why less than? Why do I have to flip that sign? So divided by negative. Okay, so do be very careful with your greater than and less than's flips from it. Otherwise, if you're always worried, go back and plug it in and choose a value higher or less than that and see what that does from it. Okay, so that's one criteria on k, is that k can't be greater than 9. It's got to be less than that. What else is going to limit k? 2 plus 2k. This term also has to be greater than 0. It's still my first column. So if 2 plus 2k has to be greater than 0, then 2k has got to be greater than what? Negative 2. And k has got to be greater than what? Negative 1. So what's my full range for k? The lowest it can be is negative 1. It's got to be greater than that, and it's got to be less than 9. Okay, so that's how I design a system. If I want something that I'm multiplying by or a proportional controller in the middle of that feedback loop to make sure it maintains stability. If k was outside of those ranges, it would make my system no longer stable. Questions or concerns about that? Okay, it's going to be slightly more challenging now. Looks very similar, except now k can be more complex. the same thing I had before, but k is no longer a constant. K is a function of s, my lovely s domain that we've been used to. So now k is actually going to be equal to kp. This is really like my proportional part, or just a constant, like we just did before. But I get an extra term too. Ki is my integral k, which is why it has a subscript I, and over s. Why would it be over s if it's my integral term? How did I integrate in Laplace domain? Yeah, I divided by s plus whatever initial conditions I had from it. So dividing by s integrates in Laplace domain, multiplying by s differentiated by it. It was, again, why we went through the pain of learning Laplace transforms. It's what allowed us to take deriving and integrating, which are complex mathematical functions, and now make them just algebra, multiplying or dividing or adding and subtracting. So instead of k just being a single value, k is now equal to kp plus ki over s, where both kp and ki are still constants, but there is this s that I've got to deal with. It's my Laplace domain s. This is what's called a proportional integral controller, because it has both some part that is proportional to it, or just is going to multiply by whatever input I have. That's a proportional gain. And some other part that is going to integrate my input from it. And we'll talk about that later in the semester, why I'd want to do that particularly. But for right now, we're just going to leave it as this and try to come up with what does that mean for our Routh-Hurwitz criterion for stability from it. So now what happens? Anywhere I have ks, I really have kp plus kis. So multiplying by that, I really get kp plus kis onto 2 over s cubed plus 4s squared plus 5s plus 2. That whole thing is my forward gain, right, for this system. That I go through ks and this whole equation from it. Now, I really don't like that this is 2 terms times this. One of this has an s term and one of this does not. So I'm going to separate them out and multiply each one by this fraction separately. So that gets really 2kp over that denominator, s cubed plus 4s squared plus 5s plus 2 plus 2ki over s onto that whole denominator, s cubed plus 4s squared plus 5s plus 2. Are we okay there with all I did was multiply each term individually? Now, if they're each term individually and I can see clearly now that they're added, what do I have to do to them to add them if they're different fractions? Yeah, I can multiply this first term here by s over s. And why would I do that? Because then I will get a common denominator. And as long as I have a common denominator, I can add, right? Like I can add 3/4 and 2/4 together, and that's perfectly fine. But if I had 3/4 plus 2/5, how I add them together is I got to find some sort of common denominator. What will make these common is if I multiply this first term by s over s. As long as I multiply the same thing top and bottom, that's totally legal algebra to do. So what does that get me? On top now I have, for my whole forward gain equation, 2kps plus 2ki over, I'm going to multiply my s out onto this term. So s to the 4th plus 4s cubed plus 5s squared plus 2s. Are we okay with that? Okay. Now it's just like you had had a single block and this was the transfer function for your single block's forward gain. So now how do I come up with my equivalent closed loop transfer function will be? Well, it's got to equal my forward gain over again 1 minus my loop gain, or in my case my loop gain is just negative of my forward gain. So using my trick that I learned before, if now it's just a unity feedback, I'm going to have my numerator the same, 2kps plus 2ki. My denominator is going to start like this, so s to the 4th plus 4s cubed plus 5s squared plus 2s. And what happened is I add my numerator to it, kp. If that confuses you, you're welcome to multiply it out. You'd be multiplying by this denominator fraction on top and bottom. One from it, and that's fine. Plus 2 kps plus 2 ki. It's basically from taking 1 plus this term, where 1 gets multiplied by this guy, but this term cancels out this one. So my 1 got me this whole thing, and then I still had to add 2 kps. Okay, so now that I know that, how do I write its Routh array? It is a what order system for my characteristic equation? 4th order. So I start s to the 4th, s to the 3rd. See if I can keep it still visible. S squared, s to the 1. I'm just going to redraw just the characteristic equation, or just my denominator over here so I can see it. 4s cubed plus 5s squared plus 2s plus 2kps plus 2ki. Okay, what's my coefficient for s to the 4th? What's my coefficient for s to the 3rd? What's my coefficient for s to the 2nd? My coefficient for s? Very good. 2 plus 2kp. What's my coefficient for s to the 0? 2ki. And you can draw a 0 there if that makes you happier to fill out that array. Okay, now what am I going to get when I calculate my s to the 2nd row? Yeah, so 5 times 4 is 20 minus 2 minus 2kp over what? Over 4. That's one term. What's my next term? I have 2ki times 4, which get me like 8ki, minus nothing over 4. So that just gets me what? 2ki. It's always really nice if you have a 0 next to it, and whichever one you're doing with that term will just get you that top number, because it's going to divide by that first one. Okay, so I really don't like 20 minus 2 kp. Everyone okay with 20 minus 2 is really 18 minus 2 kp over 4. Now, my s to the 1 row is going to make some complicated equation, which I'll deal with in a second. I'm just going to write it as asterisks right now, because I can't write small enough to fit it there without it looking like a mess. But it's going to basically be this equation times this one, minus 4 times 2ki over this big whole term. What will I get for s to the 0? Yeah, so my next term here would end up just being 0. So then when I go to my s to the 0 row, I have 2 times asterisks, 2ki times asterisks, over, minus 0, over asterisks. My asterisks can cancel, and I just get 2ki. Okay. I can already see some easy terms in my front row that are going to limit what values ki or kp can have for this system to maintain stability. So my first thing is here is that 18 minus 2 kp over 4, that term's got to be greater than 0. Right, because I started positive, I can't have a sign change for 0 if it's going to maintain stability. So what does that really mean? Means 18 minus 2 kp's got to be greater than 0. Negative 2 kp's got to be greater than negative 18. And KP's got to be what? Less than 9. What about KI? Really just had 2 KI. It's the only thing I get in this last term. So 2 KI should be greater than 0. So KI has to be what? Greater than 0. That tells me something, but it doesn't tell me everything because I'm ignoring big, fat, ugly equation here that is asterisk from it. What's that equation? Okay. I'm going to just write the top part of it because to be greater than 0, that top part is the only thing that would be 0 from it. I negated so much of it. So it's really my 18 minus 2 kp over 4 onto 2 plus 2 kp minus 8 ki. Okay? And yes, really that whole thing is over this term again, but I need this to not be 0. Because if that's 0, I don't even care what the bottom term is. I'm screwed from it. Okay. So that's got to be greater than 0. I'm going to divide this term out. So 18 divided by 4 here should get me 4.5 minus 2 divided by 4 is 0.5 kp onto 2 plus 2 kp minus 8 ki. Go back up. Greater than 0. It's a lot of algebra. These are both terms with kp. I'm going to multiply them out term by term. So I have 4.5 times 2 gets me 9. Minus 0.5 times 2 just gets me 1. 9 minus kp for one of that. And then I have 4.5 times 2 kp gets me plus 9 kp. And then 0.5 kp times negative 0.5 kp times 2 kp gets me negative kp squared. So I've done this one times this one times that one, this one times that one, and that one times that one. All of my multiples. And I still have minus 8 ki. It's got to be greater than 0. Okay. I can combine my kp terms. That really becomes 9 plus 8 kp minus kp squared. And then minus 8 ki is greater than 0. This term here, if you like it factored better instead in pretty factors, could be written as 9 minus kp onto 1 plus kp. Just a prettier factor way of that. This equation, I don't expect you to be good at knowing what that looks like in a graph, things from it, but you could always, make Excel graph it or something like that. But what it will turn out is if I were to graph with my x-axis is kp, my y-axis is ki from it, it will look like a hump, like this. With kp was already limited, it can only go from 0 to 9. And then my ki gets limited by that as well. It has to be greater than 0. And I could choose any point on here. So for example, I'm going to choose when kp is equal to 3, where this will cross on my graph is ki is also equal to 3. But you could plug that in. I could choose kp equals 3 here, plug that in, and then figure out what does ki need to equal. So if kp equals 3, which again satisfies one of my other criteria that it had to be less than 9, let's go back to my original Routh array. I'll rewrite it here. So that was s to the third, s squared, s to the 1, s to the 0, and I had 1, 4, 5, 2 plus 2 kp, 2 ki, 0. We had my asterisk equation, where I'll write that in a second, and then 2 ki down here. If I plug in kp equals 3, then when I had the term 2 plus 2 kp, what does that become? I get 2 plus 2 times 3 is 6. What's that? 8. Okay, so I'm going to erase that and write 8. Okay, now my asterisk equation doesn't become so scary, so I can write it more easily when they're actual numbers and not variables I have to keep up with. So let's go erase that asterisk first. Okay, now what will I get for S1? I have 5 times 4 is 20. Yep. Oh, you're right. I just can't write my S to the 4th. This is S squared. This is S to the 1. So my asterisk was actually down here. I'm sorry, I skipped a whole row in my writing that. Let's delete that. Let's write this a little better. Okay, so I do still have 1, 4, 5. This was still 2 plus 2 kp, which becomes 8. 2 ki and 0. And now I'll still get 20 minus 8 over 4. What will I get for my next term on what is actually my S to the second row? Just 2 ki, like I did before, or it's 2 ki times 4 minus 0 over 4. Just 2 ki. My S to the 1 row now becomes something that's not so scary. 20 minus 8 is what? 12. 12 divided by 4 is what? 3. So I can even write that as a nice pretty number, no variables. We like things that are pretty numbers without variables. 3. Now let's calculate my S to the first row. How do I do that? I now have 8 times 3, which is 24, minus 8 ki over what? Over 3. What about my next term? 0. And my S to the 0th term then becomes what? 2 ki. Again, it would be 2 ki times that minus nothing over that, so just 2 ki. That looks a lot prettier to deal with if I select a value for 1, as long as I make sure it's in my range and then move from it. So now what are my limitations on ki when kp was selected to be 3? Now I've really got to have that 24 minus 8 ki has to be greater than 0. That came from that term. And that 2 ki has got to be greater than 0. We already had that one. That was just ki was greater than 0. Now what's my limitation on ki from here? Negative 8 ki has to be greater than negative 24. So ki has to be what? Less than 3. So between 3, this way, 3 ki and 0. The key is here that if I select a different value for kp, then this number will change, this number will change, and this number will change. And it will change my restrictions on ki. Again, they lie on a continuum curve. If I could see if I change one, the other one changes from it. But you can select one and then find the other one from it. Just comment. Questions or concerns about that? Okay. So, what happens if I make kp3 and ki equal to 3? We just said kp is 3 made of limitation that ki had to be between 0 and 3. Technically, I said less than 3. If I make it actually equal to 3, what happens? Again, back in my original equation, let me get my original matrix back. Actually, let's just scroll up, we'll find it. Here's my original matrix. When I plug in both Kp is 3 and Ki is 3. Kp is 3 will get me 8 here. And then I have 18 minus 2 times 3. So 18 minus 6 gets me what? 12, which 12 divided by 4 gets me 3. And then I had what times each other. Oh, it's easier to do it on the one below that. Hold on. Sorry. So we already had 8 and 3 from it. What happens when I plug in 3 here for Ki? 24 minus 8 Ki over 3. 0. So if this is 0, this whole row became 0. What happened when a whole row was 0? I looked at the equation for the row above it and wrote its auxiliary equation and things like its derivative. What is this auxiliary equation? This is really my s to the second power. So that's really 3s to the second plus 2 times Ki, when Ki is 3, so 6. Okay, this is my auxiliary equation. If this guy gets me now in trouble by being 0. So when Kp and Ki are equal 3, then I get a row of zeros that has the auxiliary equation for the row above it that is 3s squared plus 6 equals 0. Okay? So I know that then has to be a factor in my original equation. That's when I got a row of zeros, is when this is a factor. What does this equation solve to? What does s equal to here? Okay, s squared equals negative 6. Negative 6 divided by 3 is negative 2. And then I square root that. So what do I get? S is going to equal the square root of 2j plus or minus that because I had negative. When I have roots that are at s equals plus or minus 2j, where are they on my whole graph? On my y-axis or my purely imaginary axis, right? They're up at positive square root of 2j and down at negative square root of 2j. Those made oscillations, right? If I just had those poles and nothing else, I would get a system that looks like a sine or cosine wave oscillating. That oscillation frequency itself is just the number in front of the j. It is square root of 2 in radians per second. And the period for that, if I know the frequency, which is oscillation, the period is the inverse of that. If this is in radians per second, remember radians mean going around a unit circle. How many radians are there to go around once in a unit circle? 2 pi. So I have 2 pi is really radians per cycle. And I was at a frequency of square root of 2 from it. Radians per second. So my radians cancel. And I really get like a second per cycle from that, which is a period. How long it takes to go from 1 to here. 2 pi over square root of 2, to give that a real number, is about 4.4 seconds per cycle. So if I look at this with a unit step response, if I had Kp and Ki equal to 3, I would get something that looks like this sine or cosine, where the period, time it takes to repeat this wave once, is about 4.4 seconds. So not only can I tell what level at this right off cutoff point when I would then get marginal stability, and it could go into then being unstable past that, I can tell what frequency that would oscillate at marginal stability and its period from that. Questions or concerns about any of that? Okay, let's look at this one. We've added extra complexity to our system here. Not only do I have one feedback path, I have 2. More fun, right? I can do the same thing but in little steps. So I'm going to look at this one first by itself and see what I can do with it. Again, keeping in mind my equation to convert a closed loop transfer function from a block diagram is my forward gain over 1 minus my loop gain. Okay, so just looking at the part where I have the blue circle around, what's my forward gain for that part? Be like going from here to here, the only things you hit going in a forward direction. So the only thing I hit was this, right? 1 over s on the s plus 2 and the s plus 3. My forward gain. Okay. Need to do that over 1 minus my loop gain. My loop gain does have a negative. It's a negative feedback system. So it becomes 1 plus, what's my whole loop gain? For just the blue circled part. For just this big blue circle. Should be different. What do I have to go through in that loop? I go through this whole polynomial transfer function. What else do I go through? S. Okay, so now I have something in that feedback path, and that plays a role in my loop gain, but not my forward gain. So it becomes this with an S times it. So if I have S over S onto S plus 2, S plus 3, what happens to my S's? They cancel out. Okay, I don't like the way that looks. That looks like a very ugly fraction. What am I going to do to fix it? I don't have quite the exact same denominator, but I have close here. So I'm going to choose what's the messy fraction denominator on my denominator, multiply by that on top and bottom. So I'm multiplying by s plus 2 onto s plus 3. And what does that get me? On top, what am I left with? This now cancels with this. This now cancels with this. So what am I left with? 1 over s, which is really 1. I'm going to move that s onto the bottom. And that s was, what am I left with on bottom now? That 1 has to be multiplied by this whole thing, right? So s plus 2, there are big parentheses here, s plus 3, now plus 1. With big parentheses around that and an s times that whole thing. Are we okay with that? Yes. Multiplied by the whole s on the s plus 2 on the s plus 3? You could. It's alternative either way. Yeah, I choose one or the other, but yeah, you should get the same thing. Okay, so I now have this. I'm going to distribute out my s to things because that makes me a little happier into what I'm doing. So I'm going to have 1 over s onto this term. I'm going to write it as s squared plus 2s onto s plus 3 plus 1. Okay, that really equals what? Let's multiply those out. Yes, thank you. Plus s from s onto this one. And then I have s squared times s, that is s cubed, plus 2s squared from here, plus 3s squared, plus 6s, plus s. Now combine my terms. I have one s cubed term. I have 2s squared plus 3s squared, 5s squared, plus 6s plus s gets me what? 7s. Okay, that was a good bit of algebra, but that just did that part. Now it's like I just had a single block that looks like that in place of this whole big mess. That got multiplied by k and is in yet again another negative feedback loop. So I got to do the same process here of my forward gain over 1 minus my loop gain. Except here, this is be my forward gain times k. So I'll have k over 1, sorry. So I'm going to do my little trick to do this faster. I'm going to have s cubed plus 5s squared plus 7s plus k. Again, it takes my denominator, and if there's nothing in my feedback loop, all it does is adds that denominator plus my numerator. My numerator would be 1 times. Questions or concerns about that? Okay, we now have a characteristic equation for the whole thing. So I just get to look at this denominator. Let's do a Routh array for it. So my equation to rewrite it is s cubed plus 5s squared plus 7s plus k. And I make my Routhian array s to the third, s squared, s to the first, s to the 0. I want you to put in your numbers and see if you can figure out what are the limits for k from it that would keep this system stable. Fill out the rest of that array. You get k has to be greater than something, it has to be less than something. You talk to your neighbor, see if you got the same array table, and see if you get the same range for k. How many people have an answer yet for what range k should be? Okay, few. How many? If you've got one, talk to someone next to you. Maybe who doesn't have one yet. Or if you're stuck, talk to your neighbor. Maybe a few more minutes and we'll see what we get. Okay, anyone brave enough to tell me what range they think they got for k? Yeah. Good. 0 has to be less than k, which also has to be less than 35. How do I get that? What does my first row across read? 1, and then skip over to 7. What does my next row read? 5 and k. Can't forget the k, but just treat it like it's constant. What do I get for s to the first? 7 times 5 is 35 minus k over what? 5. What do I get from my next row? There's a 0 here if you like that. I have k times 35 minus k over 5 minus 5 over 35 minus k over 5. This again just gets me k. One from it. So this and this both have to be positive or greater than 0. So 35 minus k has to be greater than 0. Negative k has to be greater than negative 35, so k has to be less than 35. Again, don't forget that whole flipping the sign if you're dividing by a negative or multiplying by a negative. Otherwise, check your number and make sure that works from it. And for this, just k has to be greater than 0. So if k is it my magical number, I already did my Routh array from it. If k is equal to 35, then what happens? In here, I would have 35 minus 35, I would get 0 over 5. This whole row would become zeros. What would be the equation, my auxiliary equation for why this whole row became zeros? I look at the row above it, what's the equation for this row? 5s squared plus k equals 0 would have to be a factor of my equation. So what does that get me? 5s squared plus k equals 0 from it. So s is really equal to plus or minus the square root of, when k is equal to 35, that becomes 35 divided by 5 is 7. So plus or minus 7j. What would be my oscillation frequency for this if k was equal to 35 and it became marginally stable? My oscillation frequency would just be the square root of 7. My period for the oscillation is again 2 pi over that square root of 7. That would be it. Questions or concerns about doing that? Okay. So we've now learned all we're going to do with Routh-Hurwitz criterion. Both proportional controllers, we can now design those for a range of a constant k value, and proportional integral controllers when we have k and a ki over f term. We can now calculate oscillation frequency based on our characteristic equation from that. Have a good rest of your week. I'm going to be posting a short video lecture that gives you a hint on one of your homework problems, your first homework problems with your Bode frequency graphs. So be on the lookout for that. But do try to do your homework because it's a little bit longer than some of them. So.